Hi, in the previous two sections, we discussed the model of firm's production and costs. Now we have the pieces needed to analyze the firm's profit maximization problem. In the next few sections, we will discuss different variations of this problem. Each variation depends on the level of competition that the firm operates in. In this section, we consider one extreme scenario, perfect competition. Some markets are more competitive than others. There are countless pizza shops in the US, but only a handful of breakfast cereal producers that splits up the entire market. There are many t-shirt companies, but only a few car manufacturers. This difference plays an important role in our modeling decisions. A small firm's decision is unlikely to have a major impact on other firms in the market, but a bigger firm's decision would. Perfect competition is a scenario economists use to model an extreme form of competition. It is a hypothetical environment constructed by a set of assumptions. The first assumption is that there are many small buyers and sellers in this market, so no individual buyer or seller has a major impact on others. Each buyer or seller simply responds to the market conditions, as opposed to being able to influence others to change the market through their own actions. Second, we assume that all firms produce exactly the same product, so no firm would have an advantage over others on the product itself. Third, we assume that all buyers and sellers have full information about price and product characteristics, so consumers don't have to search for a better price or to find a better fit for their needs. The consumers would just go directly to the seller who offers the best price. Fourth, we assume there is no transaction costs. This means there is no frictions during transactions. Buyers and sellers cannot cheat on each other. The buyers cannot bail on their promises to pay the bill. The sellers cannot renege on the promise to deliver on the product according to the specified conditions. There is therefore no need to hire lawyers to write contracts or spending a lot of resources fighting over disputes in the court. Fifth, we assume that firms can easily enter or exit the market in the long run. There is no entry barrier, such as a lengthy process of obtaining a license or a policy restriction that prohibits foreign or out-of-state companies to operate in a particular industry. Obviously, these assumptions are not realistic in most contexts. A rare example that matches well with this set of assumptions is the agricultural product market in the US. Many farmers and buyers purchase corn or soybeans in large quantities at a centralized market, such as the Chicago Commodity Exchange. The price on the market is updated and publicly displayed at a very high frequency, and there is very little uncertainty about the quality of the products. It is true that most markets in the real world don't work like this, however. But just like understanding a frictionless world helps us understand the physics in the real world, analyzing firms' behavior under perfect competition provides very useful insights about real markets. These assumptions help us abstract away from many complex details of different markets to focus on a very basic set of features that is common across different markets. The development of economic theory about firms and markets are constantly relaxing all these assumptions to model more complex and more realistic environments. We will see some examples in our reading material, but regardless of how complex those models become, these basic results from perfect competition always serve as a useful baseline to compare against. Before we go on, I'd like to note that economists use the word competitive to mean two different things when they refer to the market versus the firm. Whenever we talk about the competitiveness of the market, we're simply describing the structure of the market. A market is more competitive if each individual firm in that market faces more competition, perhaps because all firms are relatively small, or no one has a distinct advantage in their product or in regulations. This is equivalent to saying that the firm in the market have weak market power. In some other contexts, perhaps in more business settings, you may hear people use the word competitive to describe firms' decisions or strategies, such as a firm pursues a competitive pricing strategy or develops a competitive product. These descriptions refer to a deliberate choice of the firm in how to compete against its competitors, and it is not referring to the market. In this course, we will only use the term competitive in the former sense to describe the market environment that the firm operates in. When it comes to perfect competition, a very confusing point for me when I took the principles class was the assumption that each firm in a perfectly competitive market faces a perfectly horizontal demand curve. If you remember, in the principles class, we draw these graphs for firms in a perfectly competitive market, and you were told that the firm faces a perfectly horizontal demand curve. So regardless of how much they produce, the price they face is constant. Perhaps the reason you heard is that the firm in a perfectly competitive market is a price taker, and the reason for that is because they're all very small, and their products are identical. So their output choice has no impact on the market. It makes some sense, but for me, it was very hard to reconcile with the fact that the market demand curve is downward sloping, although each firm's demand is completely horizontal. Now, we would like to discuss the seemingly contradictory feature. To start that, it is useful to write down the demand curve facing each individual firm, or what we call the residual demand curve. To see what it means, let's look at these two graphs here. Imagine that you're starting out as a producer in the market of metal chairs, let's say. From your perspective, what is relevant for you is how much is the total demand, and how much of that demand is already filled by your competitors. This is exactly what the right-hand side graph plots for us. In this market, the total demand from the consumers is at 500,000 metal chairs per year, and the price is at $66. Looking at this demand, you might think, how much is the leftover demand for me, from my company? Well, the red curve here on this graph plots the total supply of all of your competitors. The little superscript O here indicates that this is the supply of all other firms. In other words, it is the total market supply minus yours. As we see that at this price of $66, all the demand is already filled by all these other firms. So how much demand is left for you? Well, it's zero. This is why the graph on the left-hand side plots a quantity of zero at the price level of $66. Now, what if the price in the market is a little bit lower? Say, instead of $66, it's at $63. At this lower price, the consumers are willing to buy more, and your competitors aren't willing to sell as much. So now there is a gap between the demand and the supply by all of your competitors in the market that you will be able to fill. And the gap in the demand is exactly the difference between the market demand and what your competitors are willing to provide. In other words, this is the residual demand. On this graph, the residual demand at the price of $63 is exactly 527 minus 434, which is 93 units. And this is what's plotted on the graph on the left-hand side. It says that when the price is at $63, the residual demand for your firm or each individual firm is going to be 93 units of metal chairs. Now let's define a notation for the residual demand so we can refer to it easily later on. we will use this notation of D superscript R to refer to the residual demand for a firm, which is a quantity as a function of the price. And it is defined to be the market demand minus the total supply by all the competitors in the market at this price level. And it is exactly describing the concept we're trying to illustrate on the graph above. Now we're ready to think about the different shapes of the demand function and residual demand function. To do that, we'll explore how the demand function and the residual demand function each responds to a small increase in price. Knowing that the residual demand is the difference between the demand and supply by all other competitors in the market for all price levels, we can take a derivative throughout this equation. The derivative says that the change in the residual demand from a dollar increase in price is equal to the change in the market demand minus the change in the supply from all other competitors. So now we have a lot of derivatives, and we will use our familiar trick to rewrite them into elasticities. At this point, we need to be careful about different quantities at the same price level. In our previous example, at the price of $63, the residual demand for the individual firm has a quantity of 93 units. The market demand is at 527 units, and the supply by all other firms is at 434 units. So we have three different quantities here at play. We need to keep in mind that when we introduce quantity level to construct elasticities, we need to use the corresponding quantities. In particular, let's denote the individual firm's demand level by little q here. Then for the left-hand side derivative to turn into price elasticity of demand, we need P over little q. So now let's multiply this ratio throughout this equation. Now we will have price elasticity of the residual demand on the left-hand side. And we will try to manipulate the right-hand side terms to the forms of elasticities as well. Notice that the second and third terms in this equation are not elasticities yet. We have the needed prices in place, but we don't have the correct quantities. The quantity of the total market demand and the quantity supplied by all the other competitors. Because little q is just the quantity of residual demand for one individual firm. But hey, we have our familiar trick to make up the needed terms by multiplying by 1. Here we denote the quantity demanded in the market by big Q and the quantity supplied by all other competitors by big Q sup O. O stands for others. Then what we can do is that we can switch in the needed quantities, Q at the bottom here, in with this P on the top, and then we will have the needed price and quantity that's corresponding to the one we use in the derivative. Then we have elasticity. And similarly here, we're going to switch in this Q sup O on the bottom to combine with the price, and then we'll have the needed quantity on the top, so we can have elasticity on the right-hand side for the third term and the second term. Now, we have price elasticity of residual demand on the left-hand side, which we denote by epsilon I, where I stands for individual firm, and this is a price elasticity, and this is a price elasticity of residual demand for that one firm. And on the right-hand side, in the first term, we have the price elasticity of the market demand, which we denoted by epsilon throughout the semester. In the third term, we have the price elasticity of supply by all the other competitors, which we denote by eta sub O. Again, O stands for others. Now, what we need to process further are these ratios of big Q to little q and big Q sup O to little q. So, what are they? Well, in this context of perfect competition, we're thinking about an environment with many identical firms. Because they're identical, the demand for each firm would be the same. So let's say that we have n firms in total, little n here, and the demand for each firm is little q units. Then the total quantity demanded in the market, big Q, divided by the little q, which is the demand for each individual firm, should be exactly the number of firms in the market, or little n. And similarly, in the equilibrium, the supply for each firm will be the same as the demand from each firm. So the supply from all but one firm will be equal to the total demand for all but one firm. And therefore, dividing the demand for all but one firms by the demand of each firm should be equal to the number of all but one firms, which is n minus 1. We can pack up all these terms into this expression in the form of elasticities. And what we have here is the price elasticity of the residual demand for one individual firm is equal to the number of firms in this market multiplied by the price elasticity of the market demand, and then minus n minus 1 times the price elasticity of supply of all the competitors. Note that the epsilon is negative because of the law of demand. Multiplied by n, the elasticity of residual demand is much more negative. Furthermore, eta is usually positive because of the law of supply. So now we further subtract a very large negative number by a large positive amount, and the elasticity of the residual demand will become even more negative. In other words, the residual demand is much more sensitive to an increase in price than the market demand. To make this observation clearer, let's make an approximation to further simplify this expression. When n is very large, just like the environment of perfect competition, n minus 1 is basically n. And the supply by all other firms is basically the supply by the entire market. Then the price elasticity of supply by the entire market is basically the same as the price elasticity of supply by all but one firms. So if we take these approximations, then we can rewrite this equation into a simpler form, which is just the price elasticity of the residual demand is approximately equal to the number of firms n times the difference between the price elasticity of demand in the market and the price elasticity of supply. Now let's use a numerical example to further illustrate what this expression implies. Given this expression and its approximation we just derived, if we have a market with 100 firms and the demand is unit elastic, the price elasticity of supply is 2, then using this approximation, we have the price elasticity of the residual demand would be 300. That's a crazy amount. When the price increases by 1%, the market demand decreases by 1%, and the market supply increases by 2%. It's nothing too sensitive at all. But with 100 identical firms in this market, each individual firm's residual demand will decrease by 300% when the price increases by just 1%. That's incredibly sensitive to changes in price. Now imagine the residual demand for an individual farmer in the market with 107,000 soybean farmers in the US. The demand is super elastic for each individual farmer. And this is why it is actually quite reasonable to assume a flat individual demand curve for a large market with many competing firms. Because the residual demand facing each firm is very responsive to a small change in price, although the market as a whole may not have a very elastic demand at all. In other words, going back to our seemingly contradictory observations, it is in fact consistent to have a downward sloping market demand curve while having a horizontal residual demand for each individual firm. Now, we'll turn to the firm's profit maximization problem. As we mentioned previously, throughout this course, we assume that the firm's objective is to maximize its profit. And the firm's profit is denoted by this notation of pi, which is equal to its revenue, R, minus its cost, which is a function C of its output level, little q. We previously derived properties about the cost function, which reflects the minimum level of cost for the firm to produce a given output level of little q. We can further break down the revenue into products of price and quantity. Then we see that the essential trade-off facing the firm is to choose an output level that balances the two forces between the revenue and the cost. When the firm's output level Q does not change the price level, then the revenue part increases in output in a linear way. If the price is $5, then every additional product sold increases revenue by $5. However, the cost doesn't usually increase linearly in the output level. As we discussed previously, the marginal cost may be low when the output level is lower, but once the output is sufficiently high, the firm starts to experience a decreasing return to scale, and the marginal costs start to increase. As a result, a reasonable model for the profit function typically looks something like this, which increases initially in the output level, but decreases once the output level is sufficiently high. For a nice profit function like this, as we illustrated on this graph, the optimal output level of the firm must satisfy a simple first-order condition, such that the marginal profit is 0. We discussed the intuition for the first-order condition in the previous video when we introduced the Lagrangian approach. It will be useful to review that video if the intuition about the first-order approach is not very familiar to you. In the principles class, we were told that the firm maximizes profit by choosing an output level where the marginal revenue is equal to the marginal cost. You may be told that this is just a rule to follow, but the underlying reason is coming from the firm's profit maximization problem. Now, let me explain a little bit further about how they're connected. If there is a unique maximum for the firm's profit, then the optimal output level must satisfy the first-order condition, such that the derivative of the profit with respect to the output level Q is equal to 0. But by our definition, the profit is just revenue minus cost. So the first-order condition is actually equivalent to the condition that takes the derivative of the revenue and set it equal to the derivative of the cost. But this is just marginal revenue equal to marginal cost. In other words, the rule that marginal revenue equal to marginal cost is just the first-order condition of the firm's profit maximization problem when the profit function is nicely shaped. The intuition from this condition is that if an extra unit of output increases the firm's revenue more than it raises the cost, then the firm should produce more output to increase the profit. While, on the other hand, if the extra unit of output increases the cost more than the revenue it brings, then the firm should dial back on its output level to increase the profit. As a result, at the optimal choice of output level, the firm must choose an output level such that the marginal revenue is equal to the marginal cost. Notice that in deriving this condition, we did not involve any condition related to perfect competition at all. What it requires is just that the profit function has a nice bow shape like this. So this condition works generally beyond the perfect competition. However, given perfect competition, we can further refine this condition. This is where the horizontal residual demand comes in. In a perfect competitive market, the residual demand facing each firm is perfectly horizontal, which means that regardless of the firm's output choice, it has no impact on the price on the market. In other words, the price in the market is a given constant for each firm that is independent of the firm's output level Q. And this implies that the marginal revenue of the firm is particularly simple, which is just the price and the price alone. The intuition is that because the firm is a small participant in the large sea of competitors, its output choice is not substantial enough to move the needle to change the price in the market. As a result, every extra unit it produces and sells just increases its own revenue by a constant amount, which is the market price level P. Because of this very simple marginal revenue, the profit maximizing condition reduces further to price is equal to marginal cost under perfect competition. But it is just a special case of the general marginal revenue equal to marginal cost condition combined with the horizontal residual demand result under perfect competition. The condition brings a lot of convenience in graphical analysis, so we will highlight it separately as a remark. We should all be familiar with this graph from the principal micro courses. Under perfect competition, the marginal revenue of the firm is equal to the price of the market. So it is a horizontal line that remains constant regardless of the output level Q. Now, given the marginal cost curve of the firm plotted in red here, the profit maximizing output level of the firm is determined by this point where the marginal cost curve is equal to the marginal revenue or price. In other words, it is corresponding to this little point E here on the graph. When the output level is lower than this point E, the marginal revenue is higher than the marginal cost. So the firm's profit would increase as it increases its output. Beyond point E, the marginal cost is higher than the marginal revenue, so the firm's profit would increase if the firm dials back on the output level. And the profit is maximized at this point where the marginal revenue is equal to the marginal cost. When the firm chooses this output level, its revenue is equal to P times Q, which is the size of this entire rectangle from the origin all the way up to the price, and from quantity 0 to the quantity corresponding to E here. And the firm's cost at this level of output is equal to the average cost at this output level, which is indicated by this average cost curve at this point of output level, which is here, multiplied by the output level Q. So the total cost will be 284 times the height of the average cost curve here, which is 650. In other words, the total cost is the area of the rectangle marked here. Subtracting the total revenue by the total cost, we would have the firm's profit equal to the size of this rectangle here, marked by an orange color. This graph on the bottom simply highlights exactly the same idea, but plotting the profit against the output level. Now let's turn to look at an algebraic example of a model where the firm maximizes its profit. Let's say we have a firm in perfect competition that faces market price P and a cost function that is quadratic. So the cost is equal to the output level squared plus 12. Then what is the firm's profit maximizing output level Q star and its profit level pi star? To solve this problem, we first write down the firm's profit maximization problem. The firm maximizes its profit, which is revenue minus cost. Given perfect competition, the price is a constant for the firm, unaffected by its choice on quantity, while the cost function is given by its quadratic expression as given here. So the firm's problem is to choose the output level Q that maximizes this expression. To find the optimal output level Q, we take a derivative of the profit function with respect to Q and force it to be 0, which gives us the first order condition. Now, can you pause the video here and try to solve the optimal output level yourself? Okay, hopefully you find the same optimal output level as I do here. And it would be Q star is equal to 1/2 of the price level. From here, we can plug in this optimal output level back into the profit function here to find out the maximum profit level for the firm. After plugging it in and a little bit of calculations, to simplify the expression, we can find that the highest level of profit for the firm is going to be 1/4 of p squared minus 12. Now, let's look at this expression for a second, which is a function of price. This profit function automatically builds in the firm's profit maximizing output choice, and it tells us what the highest level of profit the firm can earn when the price is at a level of P. And this is the profit the firm can make if it produces. However, it does not guarantee that the profit is positive. In fact, if P is 0, then the firm's profit will be negative 12. So the firm would make a loss. If P is larger, let's say 10, then the profit will be 100 divided by 4, which is 25, minus 12, which will be 13. So the firm will be making a profit. Clearly, this function is increasing in the price level in the market. In other words, there must be some price between 0, which gives a negative profit, and 10, which gives a positive profit, so that the firm just breaks even, or having a profit of 0. If we know that price, then we would know that the firm can make a profit when the price is above that threshold and a loss if the price is below it. So what is that price? Let's just impose exactly this condition such that the firm's profit is equal to 0, and this is equivalent to the price is equal to square root of 48, which is approximately $6.90. So we know for a firm in this model, it will make a positive profit if the market price is above this amount. But what if the price is below that? Should the firm follow this price equal to marginal cost rule and keep operating under the negative profit? Or should it just choose to stop producing altogether and choose Q equal to 0? It turns out that this decision rests on the timing of the firm's decision. We will continue this discussion in the next video, where we talk about long run and short run competition.